Hi, people who are here, if anyone's here. Quick recap of people who followed. There was Lahobo, thank you for following. I don't know who you are, but you're awesome for following, so thank you for doing that. And a big thank you to everyone else who's followed or tuned in so far, or will eventually be watching this in whatever form it's in. You're all cool people, and physics is a cool thing for the most part. So, today I am going to be talking about some quantum mechanics, which is the title of this stream. So let's get right into some quantum. So I'm not going to be going over any of the really principles of quantum mechanics or the basics of it. I think I'm using this just kind of as a practice environment to sort of refresh on some old skills. So this is not intended to teach you quantum from the beginnings. This is assuming you know some stuff about linear algebra and quantum mechanics already. We're going to be going over a couple questions just sort of in the vein of generic spin half stuff. So if you're rusty on your quantum, this will be a good review. Not that I'm targeting anyone in specific in that. Okay, so I'm just going to write down some questions here, and then we're going to come back to them as we get to them. So first of all, question 1. So I want to drop the size of this pen just a little bit. So given a state, and we're just going to have some quantum state represented by the... Get out of here. Some quantum state represented at some initial time, which I'm going to call t equals 0. And that state is represented in the z basis as some normalization factor times the plus. And in fact, I'm going to throw down a little z here on the bottom just to remind myself that that state is being represented in the z basis. Because these kets, Bras-and-Ket notation is very abstract, and it kind of obfuscates the basis that you chose when you wrote down the ket. So I'm going to put those little z's there to kind of remind myself exactly what I'm looking at. And I will also just say about the intention of this. I'm going to be doing most of these questions blind. I came up with some stuff, and I'm just going to run through it, and we're going to see what kind of nonsense I run into. And if I run into some nonsense, I'm going to try and dig my way out of that as sort of a more natural kind of process than just, doing something that I've rehearsed a bunch. So my goal here is really to kind of be a little authentic with the problem solving and hopefully run into some errors. So given this initial state, we want to calculate a couple expectation values. I'm not going to define what an expectation value is here. We're going to define it when we get to it in a minute. But I want to calculate a few of these. So I'm going to calculate the expectation value of the SZ operator, the expectation value of the X operator, the expectation value of SY, the expectation value of S as a vector, and what else do I want? Maybe we'll do the uncertainty in something. I'm not sure which one I want to do here. I think the uncertainty in SX might be an interesting calculation. You know what? I'm not going to do the uncertainty now that I'm thinking about it. That's just, there's already a lot of calculation here, so I'm not going to go any further with that. So let's handle this bit first, and then I'll write down further questions that we're going to do after that. Ultimately, our goal in quantum mechanics is always to write down a quantum state and then do something with it, which normally means calculate something like an expectation value, some measurement at a later time, like what are the possible measurements of the system. And my intent here is to really get to trying to ask these same questions of these expectation values at a later time t, which means we're going to have to time evolve our state. That process of time evolution is really nasty and is very dependent on what kind of Hamiltonian you have for the system, so what the energies of the system look like. But I'm not time evolving yet. I just want to calculate these at an earlier, just given our initial state here, written in the z basis. So first up, let's calculate SZ. So expectation values in quantum mechanics are brackets, which means I have a bra, the operator, and then the ket. So the way I would write this in bracket notation is to say that this is psi at t equals 0. Oop, that doesn't go there. Then the operator I'm interested in calculating the expectation value of, and then psi of t equals 0 on the other side. And there's two different ways that I can go about doing this. I can go about writing down these vectors, because kets represent vectors. I can write them as if they were vector columns, and I can write bras as if they were vector rows. I can think about these things as vectors and matrices and try and do some matrix algebra with them. I don't want to do that. I'm going to do everything in my power to not do that, because trying to calculate expectation values is, in matrix notation, often is a nightmare. Like, the gist of quantum mechanics is that you really want to try and stay in bracket notation whenever possible, because bracket notation is designed to be very easy. And because it's designed to be easy, you really want to try and stay in that land of bracket notation whenever available. And I'm gonna try and stay in bracket as long as I can here. So cool. This OneNote actually scrolls. Mine doesn't on my laptop, but that's fine. So I'm gonna plug in the kets that represent my state. So I had a 1 over root 2, and I need a bra because I have taken, I have a bra sitting here. So plus, minus, I was doing minus, right? Yeah, minus. Minus 1 over root 2, minus ket, SZ. And be careful, these coefficients out here would be complex conjugated if they were complex. Since they are not complex, I don't have to worry about the complex conjugates. The complex conjugate of a real number is a real number. So complex conjugate of minus 1 over root 2 is minus 1 over root 2. And I don't have to worry about what that operation does to the coefficient. But in principle, if I had complex coefficients on these states, I would need to take the complex conjugate. But I don't have to do that here, because as I said before, they are real. So I know that now I'm just going to write down the rest of my state, which is this. And because these are all in the Z basis, I've dropped my Z subscripts from before, but like if you see a ket without a subscript, you know it's the Z basis. That's just kind of, for spin half systems, you know it's the Z basis. And that's totally fine to drop those subscripts. It's just kind of convention to not have them there, because you write Z enough extra times, it's going to become cumbersome. And now, because I want to try and stay in bracket notation, the only way I can stay in bracket notation for this calculation is to know the action of SZ on one of its own kets. The way that we get these spin states, the way that we got them before, so these things right here, plus and minus in the Z basis, are nice orthogonal vectors like x hat and y hat, that are the eigenvectors of this SZ operator. And for traditional like spin half systems, they're also eigenvalues of the Hamiltonian, which, as we've talked about in quantum mechanics before, but not in this stream, the Hamiltonian represents something like the energy of the system. So these are nice eigenvectors of this operator. What it means to be an eigenvector, just to rehearse some of our linear algebra, so an eigenvector follows this rule. And this is one of the worst rules in physics to read aloud, but I'm going to write it down anyway because I love saying it. A on A equals AA. I love this line of math because it's awful. It is truly awful and nonsense. It doesn't tell you anything about what the actual action or what these objects actually do. It's gorgeous. I've put a little hat over the A matrix. Sometimes we remind ourselves that operators are operators by putting little hats over them, because we have a bunch of capital letters floating around in our mathematics, so like we might as well put a little something over there to remind ourselves what this thing is. So what this means is if I have the ket A, which is some vector, some column vector, if I let the operator A act on ket A, which is defined to be one of its eigenvectors, then what I get back is the eigenvalue associated with this vector times the vector. This is the statement of what it means to be an eigenvector. An eigenvector is is a vector that is unchanged by a particular operator. So the eigenvector of a matrix is a vector that doesn't rotate when the matrix acts on it. That's nice. And I might put little eyes here to remind myself that matrices in principle have multiple eigenvectors and multiple eigenvalues associated with those eigenvectors. Okay? So since the plus and minus kets are eigenvectors of SZ, I know that SZ acting on plus or minus gives me plus or minus h bar over 2 times plus or minus back, where I have just written both of the kets at once. So there's really 2 lines of algebra located on this last line, and that's fine. I'm allowed to condense more than 1 line of math into a single line because I make the rules, or other people made the rules and they also did this, so it's fine. So now I can continue here because I know the action of this operator SZ on the respective kets that are in this sum. So SZ acting on plus is going to give me plus h bar over 2 times plus back. SC acting on minus is going to give me the same thing with a negative sign out front. So I can continue writing my expectation value for SZ now. And that expectation value now looks like everything with the bra over here hasn't changed. And anybody feel free to hop in and ask a question or stop me if something I'm doing doesn't make sense. Or, even more importantly, if you see me doing something incorrect and evil as far as physics is concerned, because I would rather avoid those big errors. And also, I don't have the command written yet for tracking global errors in this channel. So now SZ acts on this thing, and I'm going to get another 1 over root 2, an h bar over 2, and plus back. And then this thing is going to give me minus h bar over 2 from SZ acting on this thing. And then that's going to give me... It's not picking up the location of my tablet, or of my mouse cursor anywhere, is it? It's just picking up where I'm drawing. That's interesting. I should keep track of that. So, what I can do is this minus h bar over 2 on the outside is going to turn that thing positive. Minus. And now I can pull, I'm just going to pull the 1 over root 2 stuff and the h bars out to the front. I have 2 copies of 1 over root 2, so I can factor 1 over root 2 out of here and here. And there's 1 over root 2's here and here. So those things are going to multiply and give me 1/2. So there's a global 1/2 out on the front. And now I have a bunch of terms, and there's an h bar over 2 as well. And now I have a bunch of things that look like plus on plus, minus on plus, plus, I did plus on plus, I did minus on plus, now I need plus on minus. Cool. Plus on minus, minus, minus on minus. Whew. God, that's a lot of words to get through that. Anyway. So, these things, we know what these things are. These are defined things that we have from some of our defining principles of quantum mechanics. One thing that we know from gross, awful linear algebra is that the eigenvectors of any what is called a Hermitian operator, which all of our operators in quantum mechanics are Hermitian, the eigenvectors of any Hermitian operator are guaranteed to be orthogonal and normalized. What that means, and they span the space for all 3 of them. What that means is that plus on plus, this thing is a dot product. This right here is, let me do this in a purple. Let's go purple. This thing, that is an awful curly brace, is the same thing as like x hat dot x hat. These things are unit vectors. That's a dot product between unit vectors, and the only things you can get from dot product between orthonormal unit vectors are 1 or 0. 1 if they're the same, because the dot product of something in the same direction as another thing that are unit length is going to be 1, or they're going to be, or the dot product is going to give me 0 because they're orthogonal. So this is 1. And, oh my, There we go. And that is 0. So all of the like ones are going to dot to 1, and all of the bad ones are going to dot to 0. And this was an awfully long time spent on getting 1 minus 0 plus 0 minus 1 is 0 times 1/2 h bar over 2. Okay. Bad brackets. I did bad brackets?
No, you called them bad.
Oh, they're bad brackets. Okay.
You said the like ones?
Yeah.
And then the bad ones.
The like ones and the bad ones. Oh. Didn't realize I called them bad. Sorry, brackets. I didn't mean to call you bad. You're just different. It's fine. So we get 0 for this expectation value. Let's remind ourselves what an expectation value is. An expectation value is the weighted average of the results of measurement times the probability of that measurement coming. So the state that I was given is a superposition or an addition of two z eigenstates. Their associated eigenvalues or results of measurement, the associated measurement of plus is h bar over 2, and the associated measurement of minus is minus h bar over 2. What's the average or weighted value of those two things if their coefficients out front are the same? You know, I'm taking the average of 2 and negative 2. The average of 2 and negative 2 is 0. And so I fully expect that this is supposed to give me a 0 and that I didn't do something bad. So I'm going to like box this little guy. And I'm going to write down this 0 makes sense. Average value should be 0. Cool. So now let's do another one. Let's do SX. So SX is basically going to have the exact same procedure to it, right? I'm going to write down the state as a bra. I'm going to put the operator in the middle, let it act on the kets, and then just do my dot products. But I'm going to recognize, or I'm going to try and stay in bra-ket notation, and what that's going to require me to do, I don't know the action of an operator on anything but its own eigenvectors, right? I know AA equals AA. I don't know what A does to B. That's a different eigenvector for a different matrix, and I don't know what its action is in eigenvector like ket land. There's no way to represent a matrix operating on something that isn't one of its own eigenvectors. I can't do that calculation. So what I'm instead going to do, so I have two options basically. I can try and write down something about all of these things as matrices, treating the raws as row vectors, treating the kets as column vectors, and treating the matrix as the matrix, and just do the matrix multiplication. But as someone who has been required to do a lot of matrix multiplication in my life, I'm doing everything I can to avoid doing that. Like, matrix multiplication is the last thing I want to do right now. And so I'm going to choose option 2 instead, which is I'm going to write down the state I'm given in the x basis. Because if I write down the matrix that I'm given in the x basis, then I actually know what SX does to it. And in fact, I have chosen, the one thing that I thought about before doing this was what state I was going to choose so that it worked out nicely in some respect or another. I have actually chosen an initial state here that is one of the other eigenvectors of Sx and Sy. This state that I've been given is actually the eigenvector of minus in the x basis. So I know what Sx does to this eigenvector. It's going to give me minus h bar over 2 times that eigenvector back. So I chose this one cleverly to avoid a little matrix algebra. I'm not going to be able to get away with that in the next one. So what I'm going to do is I'm going to realize that my state is actually plus x or minus x with Sx on minus x. And I'm going to put a little asterisk here. So, ooh, that's hard to see. Hi there, Peach. Because given state is sneakily minus x, this follows. I really like that OneNote is like interpreting my writing to make it look a little better. I've never had handwriting this good in my life, and it still looks awful. It's impressive. One of you give me an 8-ball in chat if my writing is ever going to look better than it currently does, because it won't. Okay. I know what Sx does to minus x. It's going to give me minus h bar over 2 times Sx back. So this is going to be equal to x minus... That thing acting forward is a minus h bar over 2 on minus x back, which is going to be minus h bar over 2. So let's think about that answer real quick. I got that the expectation value is minus h bar over 2, without a doubt. Okay, thank you, 8-ball. That's nice. I got minus h bar over 2. So, in principle, an expectation value can return any measurement, or any possible, like, unit full number. An expectation value does not have to return one of the possible measurements of that operator. It could return 5, or 27, or, well, with the correct units. There's nothing fundamental about an expectation value calculation giving you something that you could actually measure from the operator. But here, I actually found that the expectation value was one of the possible measurements of Sx. It's minus h bar over 2. This shouldn't surprise us, or, I mean, if it does, it might just be a refresher. We took the expectation value of one of the eigenstates of this operator. So if I'm in an eigenstate of an operator, yeah, the only thing the average value I can get from it is the result, is the only measurement associated with that state. If I'm in the state minus x, and I ask what are my possible measurements from this state, I can only get minus h bar over 2 from this thing if I measure the x component of spin orbital angular momentum. So, of course I'm going to get minus h bar over 2. There's no other possible measurements here, therefore there's nothing more interesting to our average value calculation, and we just get this. So let's do Sy. Now this is one that I can't do anything pretty with. My state does not look pretty in the y basis. It's a superposition of plus y and minus y that will have gross coefficients. So instead I'm going to detail the third way, which is matrix multiplication. If I'm allowed to write down my my kets as columns, which you can't always do, particularly if your system has not a very pretty number of eigenvectors, which is to say an infinite number of them. In that situation, you're not allowed to go into matrix multiplication, or you can, but you have to be very, very conscientious and careful about how you do it. So instead, what we're going to do is I'm just going to detail this calculation in matrix land because, like, I can do it here. I'm allowed to represent these things as column vectors because they're only 2-component vectors because this is a 2-dimensional space. So kets, or bras, look like vector rows. And the vector that I was given was 1 over root 2 minus... Okay, so my coefficients would look like 1 over root 2 minus 1 over root 2. And that's the vector column that represent, or the vector row that represents the state I was originally given. Then I can put Sy in here as a state, which is 0 minus I0 with an h bar over 2 sitting out front. So maybe what I'll do is I'll gather these in different color parentheses. So there's a purple for the ket, or for the bra. Here's a purple for Sy. And then I need my ket, which is a column vector, which is 1 over root 2 minus 1 over root 2. And then more purple brackets, because you can never have enough purple brackets. And so all I need to do with this calculation is do matrix multiplication on it. Which is to say I'm going to let this matrix act forward on the vector that I have, and then I'm just going to take the dot product of the 2 resulting vectors. So 1 over root 2 minus 1 over root 2 is then going to act on some vector, some column vector that I'm left here, which in principle it's still going to be 2 components, still a 2-component column vector, but I might need a little bit more space to write down what this will be. So 0, negative I on this vector is going to give me negative I h bar over 2, keeping the units here because I'll keep the units there. I don't like them, but I'll keep the units there. And then I'm going to pick up the bottom component here from this matrix multiplication, which is minus 1 over root 2. And this is a product, all with one another. So, now this vector is going to give me I h bar over 2, 1 over root 2. And now I'm bothered by this because this is an expectation value. No, it'll actually be fine. It's going to be fine for reasons that I don't like. So let me just detail what's going on. I'm bothered because there are i's in this column vector, and I know that expectation values are real things. They should be measurable, and I see that when I do this matrix multiplication, I'm going to get 0, and that's fine. But if I had different coefficients here, this might not work out to be 0, and these i's are going to be left here, and I don't like it. And because it's an expectation value, I don't feel like there's any global phasey stuff I can do to toss it out. So like, I'll just do the calculation and close my eyes to it. 1 over root 2 times this thing, so this is I times h bar over 2 times 1 over root 2. So this is h bar over 4 from that first term. And then this thing is minus 1 over root 2 times I h bar over 2 times 1 over root 2, which is going to give me another I h bar over 4, but this one will be negative, and I'm going to get 0. Once again, because I have this nice even superposition between plus and minus z, I have an even superposition of plus or minus z, and one of the it's only one ket represented in the x basis. I'm sort of anticipating that I have very ill-defined probabilities, or not ill-defined probabilities, but like just as much probability to find plus h bar over 2 or minus h bar over 2 if I were to make a measurement of sy. That is sort of a physical indication to me that I better get 0 from doing this calculation. And lo and behold, I do. That's nice. I like that. So I've done all three here. I've done SX, SY, and SC. So in fact, unless you're using SY basis vectors, wouldn't any SX or SC vectors? Yeah, so if I have, that's a great statement. So if I have any plane ket of any of the three operators, so if my state is just plus X or minus Z or plus Y, the other two, the expectation values of the other two operators are basically always going to give me 0, because if you look at how to write down any of the individual basis states for any of the three operators in the other bases, they always have coefficients that look like 1 over root 2, and the coefficients are related to the probability of finding a measurement, right? So if the coefficients look like 1 over root 2, the probability is something like the coefficient squared, which is a 1/2, and you're always going to find an expectation value of 0 from those calculations. Absolutely. I like it. So I can also calculate S vector, which is weird. That's a weird one to talk about. But S vector is the same thing as asking, what about SX x hat plus SY y hat plus SZ z hat, where I have basically made a vectorial thing out of, so you have a half, let me answer this real quick. So you have a half chance of plus y and a half chance of minus y, which averages 0. So it's not quite plus and minus y that you have chances of. It's really the probabilities of an outcome of measurement. So if I have a state plus x, and I measure the y component of angular momentum, I have possible outcomes plus h bar over 2 or minus h bar over 2. I wouldn't necessarily say that I have half a chance of plus y and half a chance of minus y, but I have half a chance of getting h bar over 2 and half a chance of getting minus h bar over 2. And if I take the weighted average of those weighted by the probabilities, I'm going to get 0. Did I do justice to that response? I think I did okay. But I know I can feel the ghost of my quantum mechanics professor breathing down my neck right now. Even though she's nowhere near this VOD, I'm still terrified that somebody's going to find this down and they're going to send the quantum police after me. So because expectation values are nice and distributive, I can also think of this thing as sx x hat plus sy y hat plus sz z hat. And guess what? We solved for those 3 expectation values. We know what they are. Sx was minus h bar over 2, x hat, and the other 2 were 0. All right, I want to talk for a second. We haven't done the calculation for the uncertainty in these operators, which would give us a little bit more illumination about this. But I want to look at this vector because this is really interesting to me. So minus h bar over 2 x hat means that this vector s, which represents for this state, this expectation value vector s, for this state represents something like the angular momentum vector for this quantum system. That has a very classical analog. It's something like orbital angular momentum, right? Like I have a thing spinning like this. It's got an angular momentum that points up. This is asking the same kind of question. Which direction is the angular momentum point? Each of these calculations is telling me something about the component of angular momentum in that direction. So this is the x component of my angular momentum vector. This is the y component of my angular momentum vector, and this is the z component of my angular momentum vector. Not really, though. This is the average of the x component, the average of the y component, and the average of the z component. But if I did some calculations I could do some additional calculations to actually tell me what the length of this vector needs to be. The length of the real vector s. And what I actually find out, which is eternally fascinating to me, so for this thing, this looks like something, I'll get to that comment in just a second. I have a nice, I'm just going to draw the conic section because I don't remember how to draw axes right now. So here on the x thing, I know that I have an x component of angular momentum that is minus h bar over 2 big. So this is something like my x-axis, and I don't really care what the other one is, but I'll give it a name. It's my z-axis. So I know that this vector thing, if I were to think about it as a vector quantity, because it's got x hats, y hats, and z hats, I can try and think of this thing as in 3-dimensional space. It's of course got something to do with the quantum mechanics. It's got quantum underneath it, so it's not as parsable as I'm making it seem here. But we can think of this vector because it is a vector in 3-dimensional space. So what does it mean to have an average component of 0 and an average component, or to have the y and z components have an average of 0? Well, by this statement alone, it doesn't really mean anything. But by other calculations that I could do that I'm not going to do, they have an average of 0, but they have a non-zero average distance away from the x-axis. This vector length for s is not h bar over 2 big. So my vector is not, that's purple. My vector is not just the vector that points to this dot that I've drawn. The magnitude of s, I'll even write that here, the magnitude of s does not actually equal h bar over 2 from other calcs that we won't do. So what kind of a thing is this then? Well, it turns out that what you get is you get a cone. You know that this vector lies somewhere on the surface of this conic area. This stuff in here. This is the cone surface here. Oh my, I'm doing that justice. There's a cone here, and you know that this thing has a very specific component of its the angular momentum in the x component. You know that it's minus h bar over 2. But you don't know anything about the y or z components. And what that results in is the sort of fuzzy result of this vector is that it lies somewhere on the surface of this cone. It's got a predefined x coordinate, And it has a predefined length from other calculations, right? The edge of a cone is always the same distance away from the bottom of the cone. I guess I should say it lies on the rim of that cone, not the interior of it. So I'll get rid of the fuzzy stuff because that's incorrect. I really want this to be the rim of that cone. So here's the point at the center of that cone, and this vector lies somewhere on the rim. And that's kind of cool, actually. The fact that we don't know which vector that points to the edge of that cone it is something that people refer to as quantum fuzziness, which is a ridiculous name. But nonetheless, it is referred to as quantum fuzziness. So let me get back to this. What do the quantum police do? I feel like there's some sort of unobserved state pleading the fifth joke in there somewhere. Yeah. Yeah. There are a lot of jokes I can make about that I'm not going to. But I feel there is a pleading the fifth somewhere in there. Okay. So what have we done so far? Well, we took our initial state and we calculated a couple expectation values. And we used the information about these expectation values to know something about sort of, I don't know, a geometric representation of the angular momentum of a quantum system, which is something you do a lot with more complicated quantum systems, like the hydrogen atom. And it's something that you do very, very little of with spin half systems or finite quantum systems like this because it's kind of boring, I guess? Or really what it is not informative because this conic thing doesn't actually really exist in any meaningful spatial way. You can't really measure it because quantum systems don't like to be measured. They do very strange things when you measure them. But that's fine. So let's keep going. So here's part 2. Is the pink okay? I'm just gonna switch to purple. I like this purple. I want to keep going with this purple. Galaxy colors? Oh man, I need to stay away from that. So let's move on to question 2. So question 2 here is, I think, a lot more indicative of the things that you do later in quantum mechanics, which is really a lot of find the state at a later time t. So I'm going to say, given a particular Hamiltonian for the system, which I have written down to the side. It was like the one other thing that I did. So given that we have a Hamiltonian that looks like minus g b naught sy. Given that this is our Hamiltonian for the system, find the state at a later time t. And we'll do just this part first, and then we're going to ask the same expectation value questions again, but with our wave function or our state written as a function of time. So what we're going to do is there's a very hefty procedure to finding a state at a later time t, and I'm just going to kind of loosely describe that in the abstract with a couple procedural bits, and then we're going to do each of them in turn. So, to find a wave function as a function of, or to find a state at a later time t, you need to know an initial state at t equals 0, which we were given back in part 1. And you also need to understand something about the Hamiltonian, which we're also given. So, to find a state at a later time t, you need to, 1, put state in H basis. If your professors really like you and aren't trying to challenge you, and it can be either of those things, they will give you a Hamiltonian basis that is kind of the same one that you've been working with and not make any alterations to it, so you don't have to do anything too scary to time evolve. The basis that my state was given in, my state is minus x functionally, but I wrote it as a superposition of z vectors, or z basis states. The Hamiltonian I'm given is not like nicely written in the sense that the initial state I'm given is not an eigenstate of this thing. Minus x is not an eigenstate of sy, and this Hamiltonian that I've come up with, while it has units of energy, its matrix form is functionally the same thing that sy is. So the eigenvectors of this Hamiltonian are plus and minus y, not plus and minus x. That's going to present a problem for us in a minute. Yeah, I realize I need to pan down because my video is going to cover up that. So the other thing we need to do, not only do we need to put the state in H basis, we need to then do some superposition things. I'm just gonna like copy this over here because I don't want to like run into the camera feed. So we gotta put the state in the H basis. We gotta then give each basis state. I don't really know what language here. Give each basis state a time factor of e to the minus I e n t over h bar. What we're really implicitly doing in the background here is solving an incredibly complicated, well, not that complicated in the grand scheme of things, but a pretty complicated differential equation known as Schrodinger's equation, which controls how states evolve in time. Basically, the way time evolution works, or the way that any physicist meaningfully remembers what the Schrodinger's equation tells us, is that states evolve in time by putting them in the Hamiltonian basis and sticking this factor out in front of them, and that's a time-evolved state. And when I say out in front of them, I mean for each state in the Hamiltonian, or for each state for each basis state in the state you're given at t equals 0, you need a corresponding factor where this en is different for every like state in the superposition of Hamiltonian states. So this is not some global thing that we can just stick out in front of our state and call it good. Each term, each ket in our state is in principle going to have a different one of these. And we need to pay attention to that, because then we get nasty cross terms from our calculations, and everything goes to hell, and that's what quantum mechanics is. So, first of all, we need to put our state in the H basis. How do we do that? Well, we gotta find the H basis, which means we need to do some time evolution stuff. Which means my brain just shut off for a second. I don't know why I said that. We gotta find basis vectors. We gotta find the eigenvectors and eigenvalues of a matrix. How do we do that? You go to a math department, or you watch me do it here. So here's my matrix. So first things first, find the eigenvectors and eigenvalues. Yeah, actually, that's a wonderful comment, and my brain sort of exploded there for a second. So, to do this in general, to do number 1 here, put the state in the H basis in general, you have to find the eigenvectors of the eigenvectors and the eigenvalues of the Hamiltonian you're given. Because I gave myself, thank you, Maggie, for the reminder. Because I gave myself a matrix that I actually, this Hamiltonian that I gave myself is a just a constant times sy. And so I actually know the eigenvectors and eigenvalues of this thing right off the bat. But in principle, what you would need to do is you would need to find the eigenvectors and eigenvalues of the Hamiltonian you're given. And then you need to put psi of t equals 0 from whatever basis you were given and write it down in the basis of these new eigenvectors you found. So you got to put it in the Hamiltonian's basis. And then once it's in the Hamiltonian's basis, then you can, you know what I'm going to do? I am going to make this just a little bit smaller, and I'm just going to shrink myself down on the screen just a teeny bit, because my forehead's already gigantic. It doesn't need to be any bigger. Okay. So, should have done like a 1,000-yard stare into the camera at that one. Okay. So in general, you would have to put your initial state that you were given into the basis of the Hamiltonian. And that is often a really nasty process in terms of just like solving some like two unknowns kind of system of linear equations. And I don't want to do that, so I gave myself a better Hamiltonian. So, since we're given a nice H, beautiful H, gorgeous H, we don't need to so this process right here, finding the eigenvectors and eigenvalues, is known as diagonalization. So we don't need to diagonalize. No need to diagonalize. Cool. So we don't need to diagonalize H, which is to find its eigenvectors and eigenvalues. So instead, I'm just going to start working with H. So H is minus G B naught Sy. And that tells me that its eigenvectors are plus and minus Y. Because none of the constants are going to change the eigenvectors. They're just going to scale the eigenvalues of this matrix. And their associated eigenvectors, or eigenvalues, so here, let me do this in a slightly different color, just so it looks a little different. So here are the vex. And over here, I'm going to write the associated eigenvalues. So the eigenvalue associated with this is going to be the same eigenvalue of Sy, which is plus h bar over 2, times the stuff that was out here. So it's minus G B naught h bar over 2. And then the associated one with this one is going to be minus G B naught times minus h bar over 2, which gives me G B naught h bar over 2. Cool. So these are the eigenvectors and eigenvalues of the Hamiltonian that I've been given. And my state that I have, that I was given at t equals 0, is not written as a superposition of the Hamiltonian's eigenvectors. It's the plus x basis that it's written, or it's the x basis that it's written in. So I need to take my initial state, which was minus in the x basis, and I see you, parenthesis, trying to sneak away. Don't try me. And I need to turn this thing into the y basis, which in principle could be very, very gross. I have a textbook that I can open up to my spin half stuff. What chapter is spin half in? Uh-oh, I should have left this open. 2? Is that early? Operators and measurement. Ooh. Is he even going to tell me this in this book? How to write them in... Okay, so he told me how to write it in the z basis, which is not really what I want, because I would really like to not calculate this. My guess is maybe I can infer it.
How to write it in the y basis?
Yeah. It's just like, where are the i's gonna go is the problem.
There's no i's if you write it in the y basis.
Sorry, if I write plus x in the y basis, or minus x in the y basis. Yeah, yeah, she made the face because this is not a pretty calculation. But that's okay. So, what I might do is recognize that I bet I can, you know what? I bet I can do pattern matching. I bet I can do it. So minus looks like, in the z basis, it looks like 1 over root 2 times plus minus minus. So get a little dot for any basis. And plus or minus y, plus or minus in the y basis, looks like 1 over root 2, and it's plus or minus I minus. And so if I have minus x, the linear combination that I need to take, oh god, I really don't want to do the linear algebra for it, man. So I can, just sub twice means go from x to z and then z to x, right? But I would have to then solve for what plus looks like in terms of plus and minus y, and what y looks like in terms of, is that what you're suggesting? Okay, fine. Okay. So often what you have to do in quantum is like kind of YOLO it and just brute force do some substitution to change things into different bases. And there's just no damn good way around that sometimes. If you're clever or you don't have eyes sitting around in your expression, you can probably get away with just looking at it and trying to figure out what it's going to look like. I do not have the luxury of that. So What I'm going to do is I'm going to write the state I was given at t equals 0 in the z basis, and then I want to solve for what plus and minus look like in terms of the y basis. So plus as a ket in the y basis, or as a superposition of y states. So I have a plus here, and this is plus or minus y. So I can get plus by adding plus and minus y together, and then dividing it by 2, basically, and normalizing. So I can tell the first one already, 1 over the square root of 2, 1 over the square root of 2, is going to be plus y plus minus y. Do I believe that? So if I add plus y and minus y together, I get basically 2 copies of plus. And then I just divide by it. We'd love to see it. Yeah, we do. We do. It's quantum time. Wait, is that Rosemary? Oh, hi Rosemary. How's it going? Having a blast? Also studying quantum? Yeah. Yes, hi. I'm doing something. I don't know what I'm doing specifically, but like I'm doing quantum stuff, so if you want to hang out, you're welcome to. That's why I'm not just talking to Maggie, because Austin left. Austin left me. So, like, it's tragic. My life is tragic. So, what I've been doing here is I've actually been doing a simplified version of the question that y'all got on your quantum homework. So, rather than a Hamiltonian that was a bunch of generic garbage of, like, B.S, I just stuck with one of the components, Sy. And I'm trying to time evolve a given state of minus x and figure out some expectation values as a function of time. So this is kind of what I'm doing now, which is very in line. Yeah, it's the gross problem, but it is like the very toned down version of that problem. So, yeah, this is what I've been doing. There was a lot of other stuff before that, but basically what I'm trying to do now is I'm trying to write the original state I was given, which is minus x. That was the initial state I started with. And I'm trying to write it in the basis of the Hamiltonian so that I can time evolve it. And I'm just doing it all in Brockett land. So if your Brockett is a little, a little on the low side, this is a real good way to practice, is just by kind of trying to stay in Brockett as long as possible and not go to matrix land unless you have to. Okay. So I just kind of pulled out of a hat that plus z written in the... So basically what I'm trying to do right now is I'm trying to write this state in the y basis, and it's kind of a pain in the ass. So plus is going to look like this combination of plus and minus y. And please, 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 please feel free to ask any questions if you're just hanging out. Because as I swear to God, I don't actually love the sound of my voice as much as people think I do. So now I need to figure out minus written in as a term, as a combination of plus and y. And the way that I'm gonna do that is by winging it. So if I did plus y minus minus y, I'm going to pick up 2. I'll write it. I won't try and do it by sight. So minus is, so if I did the combination, say, plus y minus minus y, I'm just trying to figure out minus z in terms of y stuff, and I'm just kind of adding them together to see if I can find a nice way to do it without having to solve for it like you did in that homework problem. So plus y minus minus y up here is going to give me 1 over root 2 stuff times, so plus y is plus I minus, minus is plus minus I minus, and so plus minus minus, this is impossible to follow by language, I know, is going to get rid of the plus stuff because the subtraction is going to take away the plus cats. And so what I'm going to get is I'm going to get I minus 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 I minus. I swear that's what I get. And I get 1 over root 2 I times 2 minus. And so the way that I would normalize this is by dividing everything over here by 1 over root 2i, which I definitely knew from the beginning, and I just didn't think about it. No, is it 1 over root 2i? That I becomes a global phase. I guess it's okay. So this looks to me like writing down minus as a superposition of y states is going to be 1 over root 2i plus y minus minus y. And I'm covering it up again. Aha. Okay. So now I have the plus z and minus z kets written in terms of plus y and minus y kets. And now I can write down my x state that I was given in terms of the superposition of these two things, because I can just substitute them in from up here. So my function at t equals 0 looks like, is equal to 1 over root 2 plus, which I solved for here, which is 1 over root 2 plus y plus minus y. Minus my description for minus from over here. So I'm just copying this equation down and trying to substitute in the pieces that I solved for down below. So now minus the minus ket was 1 over root, not enough room, 1 over root 2i times plus y minus minus y. And I know this is actually going to turn out to be something like not totally horrible, but it's close enough. So I can factor this to be 1 over root 2 times plus y minus 1 over I. Oh no, that's bad. So it's plus y, 1 minus 1 over I. 1 over I is minus I, right? So this is really 1 plus I. Yeah, I believe that. Minus, if I gather, or plus, if I gather the terms on minus y, I have a positive 1 over root 2 plus 1 over root 2i, which is going to become 1 minus I. I swear it works. So these are actually, and this should be normalized, shouldn't it? This is already normalized because I kept everything in bracket notation. So this state down here is what I will call minus x, y. That's right. I put parentheses around it and just called it good. This is the state minus x written in terms of y basis states. So this is a really gross looking thing, but I need it to actually time evolve my state, because the only way I can time evolve, as per my rules back up here, is to put the state in the Hamiltonian's basis, which in this case is the y basis, and then just sort of like brainlessly and arbitrarily give every basis state that's there a time factor of e to the minus I h bar, e to the minus I e t over h bar. So, you do like a little big cross out. Moving on. So now we can time evolve. Oh. Wait, what? That wasn't what I meant, Rosie. I meant ask a question in chat, not ask me a question by text. But I understand that this was much easier for you. I'm in the middle of a lecture, actually. So I made it. It's okay. I'm not harshing you. It's not even loading very quickly. Is my phone almost dead? No. PDF's just taking forever to load. I'll get to it in probably like a little bit, but I want to continue a little bit with my... Sure. You might be able to. You might need to be permitted by Maggie, but give it a shot. And it'll tell you, why are you doing that? You're doing evil things. And then Maggie can give a permit through... No, you can't, because you'll have to open up... You can try. Give it a shot. This is an experiment for us all. So, continuing with this procedure for a couple minutes. So, we can time evolve our state now because we have it written down in the correct basis. So, psi, as a function of t, and this is, I'm going to write this as a fancy statement real quick, is the sum from n equals 1 to 2 here, but like the number of states that you need. Time evolution looks like Cn at t equals 0, e to the minus I, e n t over h bar n. That is your time evolution, like, big super equation that you need to just kind of have floating around in your brain. And this looks actually a lot better in the situation that I was given here. So my psi of t for given system our wave function is a function of t. Looks like this thing. Finding the ground state energy is a ground state wave function for a particle of mass m experiencing the potential blah. Oh yeah, I remember that question. We were helping somebody else with it a little while ago. I can get to that in a min. Let me time evolve this, and then I can segue for a sec. So just get my time evolution here, so I can like have a bit of closure about this, because otherwise I'm not gonna make that joke. Not making that joke. It's fine. So for our given system, we're going to see that we have a plus y and a minus y. So it's going to be, I have a global 1 over root 2. And then I have, on the plus y stuff, I'm going to get e to the minus I e plus y t over h bar times the coefficient, times 1 minus I, 1 plus I, actually it was for the plus, times plus in the y direction. And that's what my state looks like. That's what the first component looks like. Now I have to add the second one, which is another e to the minus I, e minus y, t over h bar, times 1 minus I, minus y. And that is my state at a later time t. Notice that e plus y and e minus y, these exponents look very similar, but they're not the same. The eigenvalues for these two are different, which means the two states have different energies, and if I were to plug those in, they have different energies, right? So those two things, those two time factors are different, and you gotta keep track of the fact that they're different. One thing that I can do, though, is I can recognize one of my freedoms in quantum mechanics is dealing with an overall phase. So I can deal with overall phases by factoring one of them out and tossing it away, because global phase on the state doesn't mean a damn thing. You can't measure it, you don't notice it in any of your calculations, it just goes away. So one thing I can do to simplify this calculation, and I know I didn't tell either of you while you were working on a similar homework problem that you could do this, but you can, and it makes it a lot easier. Well, easier. Is I can turn this boy into 1, and then this will be, so I can pull e to the stuff on the first term out in front, and then toss it away, so the coefficient here becomes a 1 times 1 plus I plus y. And on my second term, I pulled this out from both terms, I factored, which means this exponential is going to get a positive of the stuff in parentheses here. So what that means is that the second exponential is going to be e to the minus I, e minus y minus e plus y, t over h bar. And if you don't believe that the exponential is going to look like that, oh, hi, lo-fi beats to chill out, relax to, that now has lyrics in it. So There's just like some people randomly talking in the background, like about taking a trip to LA. It was very, very confusing. Okay, we're good. So, T over H bar times 1 minus I. I want this stuff to be like slightly more. Maybe what I'll do is I'll just bring the E down. Hey, look at that. I could just bring the E down. 1 minus I minus Y. Okay, cool. That's the time evolved state. That is the time evolved state. And I have tossed out the front coefficient to sort of use the freedom of what's called the phase freedom to set the first component to always be real and get rid of its quantum phase. And then just figure out what the second component is. You'll notice that when you did the nasty version of this problem, you got things that look like cosines and sines of frequencies that had energy differences in them. And this is a really easy way to see why the energy differences come up, because this thing is the difference in the energies, and it's just in the coefficient for one of them. But now the cross terms get a lot easier when you go through and calculate expectation values and stuff, because you don't have something nasty sitting out front of this term. Okay. This is the time evolved state. I'm going to answer this question that was in chat because, like, what else am I doing with my life? So, the thing you're given, and mad props for, like, typing out all the parentheticals to get this potential. So, segue to a different quantum problem really quickly. So, we're given a potential that looks like m omega squared over 2 x squared minus beta x. This is the potential. So, I mean, like, and our goal is to find this energies and function for a particle of mass m. So, given, find eigenstates, ground state, not eigenstates. Ground state, function, and energy. Okay. I really dislike how much emphasis, like, writing while streaming puts on, like, the way I write letters, because people have memed on me for, like, my entire life about the way that the process by which I write letters.
How
like,
hard do you push?
I don't push that hard. Why?
Because I could hear it.
You can hear it squeaking? Well, that's fine. Pen tips are made to be destroyed. Okay, so we're trying to find the ground state energy. And so this is a classic... How mean do I want to be here? This is a classic, like, useless quantum question. Because it's a question that is like, can you do sneaky proofy things that are mathematically relevant? But it really has nothing to do with any of the things that you, like, calculate in quantum mechanics. Like, this is just kind of this is what I will call a trick. This is a trick question. It is not, all of quantum is not useless. I will change your mind. You're entitled to your opinions, even if they are wrong. And quantum is awesome. Take it back. So, this, basically, the gist of this is hand waving. This is a question all about hand waving and saying things look close enough like other things that you end up fine. Okay, so let's talk about this. So the first thing I want to do, actually, is I want to do something horrible that I actually need. Can you look up the formula for completing the square? Because I literally never remember how to do this. I want to put this in a place that looks better. Because right now, just to explain my thinking, Rosemary, is that this thing, this guy, this boy equation right here, looks a lot like the potential for a harmonic oscillator. It's close. This beta term is nasty, and it's not quite a harmonic oscillator, but it looks pretty similar. I think completing the square is something like it's like x minus b over 2 squared plus she minus b squared over 4. Something like that. X, it's plus b over 2?
Well, you add it and subtract it.
You add it and subtract it. Okay. That's not... That's not helpful to me right now. I need something that's a little bit more procedural than that. There's just a formula that I follow, and I don't remember where it is. I would suggest not looking at images. Scroll down and just, yeah, that. Wikipedia has a great scroll down. Sorry, there's another monitor way over here that has just, there it is. So x plus bx plus c is, okay. So it turns into x plus half b squared, which is what I had, plus c minus b squared over 4. I think that's what I wrote down. Hey, that's neat. I actually knew it. Okay, so what I'm going to do is I'm going to recognize that this is a polynomial, basically of the form m omega squared over 2 x squared, right? All this stuff has powers of x. And so there's no constant power, so I don't have to worry about the constant here. Or do I want to do this on the Hamiltonian? Do I want the Hamiltonian to look? I would think I want to do this with the Hamiltonian, not with, okay. So I'm going to write down what the Hamiltonian is, which is going to be the potential plus the kinetic energy. So the potential is this v of x thing. So m omega squared over 2 x squared minus beta x. That's the potential. And then the kinetic energy is a p squared over 2m. This thing, this Hamiltonian, you can see its powers of x, right? It has an x squared, an x, and a constant term. And so I'm just going to rewrite this thing as if it was this thing, right? I'm going to complete the square in it. Basically, the reason that I want to do that is I want to look at this thing as if it was still a harmonic oscillator and just see if I treat this like it's still a harmonic oscillator, if I can identify what kind of pieces of it change to see how the ground state wave function and the ground state energy are going to change. The hint for this is that in little tiny writing at the bottom of the problem, you're told you shouldn't have to do much calculation, which is usually a hint for you have to do some garbagey hand wave thing. What, 4 out of the 10 times in physics when you have to do garbagey hand wave things, it usually has to do with completing the square. So like, it's just if you feel like you're missing something, try completing the square. It almost always works.
Or doing like fractionalization.
Or yeah, or what's that called? There's a name for it. Where you do, you have to do it when you're trying to combine bases of things that are different fractions. It's called base something, changing base. Yeah, there's a thing that you do with like a over 1 fraction plus b over 1 fraction equals c over the combined fraction. I don't know.
Oh, no, I was talking about the opposite, where you have to undo a combined fraction.
Oh, you have to undo the combined fraction. Oh, that's, yeah.
You have to undo common denominators.
So my squared term, so this is of the form alpha x squared plus, well, beta x. It's of the form ax squared plus bx plus some constant. And so what I really need to do is it's b over a, b over a, and c over a. Just to complete the square here, because like, actually I can leave the coefficient out front, and it becomes b over square root a or something, if I leave the a there. So this thing will look like x plus b over 2a, a squared, root a. Still want the b there to look the same. Yeah, I think it's going to look like that, right? The b term is going to have a power of a that I don't want, so maybe it is supposed to be this. So then I get b, 2bx over 2a times a gives me bx. That looks right.
So you factored out an a.
I factored out an a. I think it's fine.
Okay.
Basically, I just don't want I really don't want to carry this a around, but I think I have to make it look like I want. So I was going to try and divide by the a, but then I'd have to divide the Hamiltonian by a on the other side, and that's not like, I don't want to do that. So it's going to look like this, plus c minus b squared over 4. And now I can continue, because that's going to look like, well, I know what A is. It's m omega squared over 2. X plus, well, B is negative beta. Negative beta over m omega squared over 2. Squared plus. And then plus some constant stuff, which C was p squared over 2m minus b squared over 4 is b squared is beta squared over 4. Okay? So I just want to gather some terms really quick and just try and identify what we have here. So m omega squared over 2, this combination of things, I'm just going to trust that beta over m omega squared has units of position. I could check, but I am pretty confident it will. So this is something like some shifted position, right? Beta over m omega squared. So this thing is beta over m omega squared. There's like a 2. It's just some shifted position. It's going to have units of position. It's going to act like a position. And so I'm going to call it some kind of position thing. The p squared over 2m is still hanging out. And so what I'll probably do is pull the beta squared over 4 right here. And then plus p squared over 2m. Okay. What does this thing look like? This out here in purple, this is still the momentum. This is still the kinetic energy, right? The momentum p squared over 2m is still the kinetic energy. This stuff all the way over here is the potential energy written slightly differently. So if I let this thing, like, how do I want to say this? How do I want to say this? How do I want to keep going? Do I want to let this act on a state? That seems like a bad idea. I guess I could. So I almost want to, like, I almost want to stop here, actually. And I know that sounds really goofy because I haven't done anything yet. But hear me out, Rosemary, if you're still listening. Why we need to complete the square. Okay, so here was my idea. So let me, I tried to highlight this a little bit, but I talked really fast through it and didn't spend very long talking about it. So my idea is, if we want to do a problem with very little math calculation, which really means, like, wave your hands at it, then basically what I need to say is, like, okay, this is still going to look like a harmonic oscillator. So I want this thing that I've written down, I want to put it in a form that looks like a harmonic oscillator still. This beta x term does not look like a harmonic oscillator. When I turn it like this, this term, this first term, looks like a harmonic oscillator, right? It's m omega squared x squared. Are you okay with that? The x functionality, because I've completed the square, has now been sucked inside of that parenthesis. What's left here is just some shift. This is just some number. It's just some shift. I don't know what it is. Beta squared over 4. It's got units of energy, right? Like it's something. I don't know exactly what it is. But it's there. And so what this looks like to me is this looks like a harmonic oscillator with two features that are different. This looks like the term in peach. This looks like shift to the ground state energy. Right? What this Hamiltonian says is all of its fundamental structure to me is still like the same. It still looks like a harmonic oscillator. It's got some XE position term, and it's got some momentum stuff, and then it's got this constant shift in it. And I kind of feel like that constant shift probably isn't going to do anything to my eigenstates. If I actually solved this differential equation, it might, but I'm sort of like kind of pulling it out of my ass that it's not going to actually affect anything. Because this is a hand wave, remember?
You could graph it.
I could graph it. I could. Well, I'm going to get there in a sec. So this thing to me looks like a shift to the ground state energy. The rest of what's in here is a p squared over 2m plus an m omega squared over 2 and some x looking stuff. The rest of what's here is just the harmonic oscillator. Hi, Juno. How's it going? Do you want to be on the tablet? You want to be on the tablet really bad, don't you? Or do you want my lap? I think she wants my lap.
She wants to show off her kitty bee hole.
She wants to show off her butt on the camera. Yep. Yep. You can sit down. Yep. Here, let me give you just a little bit more room to sit. There you go. So the rest of this stuff that's sitting here is X stuff, X and P stuff. It's just the harmonic oscillator that's left over. But what has happened in the purple? Kitty tail. Hi, Austin. How's it going? What has happened in the in here is that this is like something like a coordinate shift. So it's been shifted. If I were to actually look at what the potential looks like, if I were to plot V of X as a function of X, you know, for a harmonic oscillator, it's going to be nice and symmetric. It's going to touch like 0. It's going to go through the origin. It's just a real nice looking parabola, right? I think you've seen you've graphed the harmonic oscillator before, Rosemary. So I think you've seen this function before. This new one that I've been given, this new V of X, what's that thing going to look like? Well, I can look at it from back up here and see that m omega squared x squared minus beta x is a parabola that has been kind of shifted in a linear way. So everything on the left-hand side of the origin is going to be shifted up by a linear amount beta x, and everything on the right-hand side is going to get shifted down by a linear amount negative beta x. So what this harmonic oscillator is going to look like to me is it's centered at x naught, and everything on the right side is kind of shifted down, and everything on the left side is kind of shifted up. So it's going to look something like this. And it's not supposed to be super symmetric. I was trying to make the left-hand side shift up and the right-hand side shift down a little bit. But you're going to functionally get a wave function. Your potential looks like that. To me, that still looks like a harmonic oscillator. Nothing about that is different, right? Like it's still a curvy thing. It's got a bottom. I can fit wave functions inside of it just like I want to. You know, it'll be stuff. You know, those pictures. Those things are still going to fit nicely. You're still going to have the same types of wave functions. The difference now is that the center of your harmonic oscillator is now at x naught rather than being at x. So to me, you're going to have the same ground state wave function. It's just going to be shifted over by x naught. That's kind of it. Did I answer that, Rosemary, to any sufficient degree? I don't know if I actually answered that to any significant... Okay, yes. I'll take a yes. Do you have any further questions about this example? Because, like, I don't... It's very hand-wavy, right? Just to like, recap the couple bits we did there. So, bit 1 was, I'm going to complete the square because I want this thing to look like a harmonic oscillator still. Bit 2 is that now that I've made it, I've kind of smeared, I've messed with it a little bit to make it look a little bit more harmonic oscillator-y. Now I can recognize that the x coordinates have been shifted a little bit, and the energies, because the Hamiltonian has this constant addition in it, have been shifted a little bit too. And that's like literally the whole problem. You can go through more steps if you really, really want to. And you can do things like trying to see what this does to a ground state wave function and see if you get anything nice back. There was someone else in your class worked through the algebra on this a while ago, and they were a little more thorough with the calculation, but I think it was totally okay. Wait, that's the ground state energy or the wave function? Where?
Neither is up here.
I don't think I have... So I circled this peach thing because it's a shift to the ground state energy. The wave function is going to look like the ground state wave function for the harmonic oscillator, which is a Gaussian, I think. Or yeah, I think it is actually just a Gaussian. Except it's going to be a Gaussian that rather than centered over the origin, it's going to just be like shifted a little bit to be centered over X naught, because your new, the addition in this potential is basically shifting where your origin is, and that's like all it's doing. And I will say that I'm responding to this question with like about 70% certainty that I'm doing this the right way. This just feels like a bow thing to me. And Austin can confirm or deny whether this feels like a bow thing, but this feels like a pretty damn bow thing to me. Where it's just like, I don't know, take your function and mess with it. Yeah, okay, thank you. It's just like, take your function and mess with it and see what you figure out. And that's just like the whole thing. Yeah, take a normal thing and just like brutally butcher it. And make it do something else. For the record, to the one or two of you that are listening, whatever you're texting, either myself or Maggie, I can't read right now because I'm not looking at my phone. So if you have questions, it might be wonderful, Rosemary, if you posted them in chat rather than trying to meme at me. Although I know you're all just like dunking on me right now, so it's fine. Ooh, shit. That was loud. Rosemary, do either you or Sophia have additional questions about this question? Actually, don't respond to that statement if the additional question is do part 2. How would we use this Hamiltonian to find the ground state wave functions and energies? How would you actually do it? Or how would you, when you say like, what am I trying to say? I have described the process by which you would find the ground state wave function, because it's the normal, with some text argument, this complete the square and circling some stuff and recognizing what the pieces look like. Like, hey, this is a harmonic oscillator potential that's been shifted to the right. This is a thing that looks like the ground state energy having stuff done to it. So the ground state wave function, by some hand waving, is going to look like the same ground state wave function for the harmonic oscillator shifted to the right to be on top of X naught. So I'm not even sure you would like necessarily write it down as much as you could just say it's the same function shifted to the right. Is 8.314, is that is that R? Or is that the value for R, or is it the value for the chemistry one? I think it's R. Okay. I know some things. I know some numbers, like 1, 2, 3, the charge on an electron, and R, apparently. And that's about it. I figured that was you, Sophia. Did I answer that question? Yeah, R is the chemistry one. Like, it is the chem one. Yeah, I'm a KB person, but I fully respect those who use R. I didn't when I was younger, but everyone's a shithead when they're younger. Did I actually answer that question, the two of you? Or do you, like, want more talk about it from me? Because, like, yeah. Yeah, and then the shift to the energy is just like, hey, look, the Hamiltonian has an extra term in it that has no functional dependence. It's a constant. So that's probably going to make the energy go down by exactly a beta squared over 4 for the ground state energy. I'm still confused on the ground. Find the ground state function. Okay, so let me highlight. Let me first say what you would do normally to answer the exact question that you have been asked. So to find the ground state wave function, to find the function for the ground state of this new Hamiltonian, you would have to solve the damn differential equation. That is how you would do it. You have to solve the ground state, or you have to solve the differential equation and find the first eigenvector for it, which is to say the first solution that you can find with the lowest energy. That is a nonsense pain in the ass, and in fact, you're not even guaranteed that that differential equation is solvable in a nice way. Don't solve that. Don't solve that. It's really, I mean, like, you would go over it in capstone quantum classes or in like a differential equations class in physics, like a math methods class, how to do that. And it requires series solutions, and it sucks. It sucks. So instead what you do is you already know the wave functions for the harmonic oscillator. So the words find the ground state function don't mean solve for anything. It means tell me what the function should be. And what the function should be, because the new potential we have looks exactly like a harmonic oscillator's Hamiltonian with some slight modifications, you make the statement, hey, I massaged this expression. It looks basically like the Hamiltonian did for the harmonic oscillator with small changes. Those changes are the energy levels have been shifted down by beta squared over 4, and the functions, the x coordinates, have been shifted over by x naught. So the ground state energy is going to be 8n plus a half h bar omega. 1/2 h bar omega minus beta squared over 4. And the ground state wave function is the exact thing that you could look up in your textbook, quantum, the exact thing you could look up in this QM textbook for what the functions look like for the harmonic oscillator, just shifted to the right. So whatever the mathematical function for the first eigenstate is for the harmonic oscillator, just like write that damn thing down with x minus x naught wherever you see the x. Did that make sense? Okay, I see a yes from Sophia. Did that make sense to you, Rosemary? Or, I mean, we can talk about it more. I'm fine trying to put like a little bit more words to it. Because I have a cat on me, and I can sit here forever.
Dude, she's been so angry all day.
Yeah, she's having a blast. Yeah. So hopefully that answered that question a little bit. Is there? Yeah, no, she wants to be in the spotlight, and that's okay. Don't we all? Hi. Are there any other questions you two had about that homework? Or would you like, or would you, are you good? Because I'm okay talking about more specific quantum stuff, or I can just like go the whole thing. Yeah. Okay. What do you mean the whole thing? So I was doing a basically subset of the nasty problem you turned in for homework last week. I was doing an easier version. Are you okay? What are you trying to do, sweetie? Are you trying to roll over? I don't understand.
Well, I gave her a bunch of catnip because she was acting like a spaz, so...
Okay, so she's all catnipped up and just wants a lap to sit on. That's fine.
Yeah.
So the ground state energy would just be the normal oscillator ground energy while subtracting beta squared over 4. Pretty much. I would write that sentence down both in English and in mathematics. So I would say like, hey, I wouldn't just... Because this is a hand-wavy question, you have to like write a bunch of hand-wavy words. So you like have to write down... what am I trying to say? Part of the argument is in the words that I was using, right? So it's not, you can't just write down, the ground state energy will be this, like make sure that you supply the pieces to get to that point. Does that make sense? I'm just making sure that I'm communicating the extent to what you need to like write down for a good answer. Okay, I just wanted to like make sure that I said that because it is important and part of the argument to have the rest of the bits there. You said yes, please, Austin. What were you even saying yes to? The ground state psi is usually... Yep, that's a Gaussian. Yep, that's what I expect it to be. So rather than x squared, it's going to be x minus x naught squared, Sophia. Redo the whole thing. What whole thing? The this question? Or like where I started earlier from doing a different question? You know what? Actually, you're baiting me. You're baiting me. I can tell. That's a bait. And I'm not falling for it. Yeah, there it is. Okay. Did you know?
We scheduled the stream. They could have come over.
What? Yeah. Yeah. Hey, this, you know what? Functionally, this was scheduled. This stream was scheduled, and you could have shown up earlier to this or something, so, although I know Austin has a life, which is not to say neither of you two have a life, but Austin specifically couldn't be here. I just, like, I don't know if I should just go back to what I was doing, or if y'all want me to do more stuff. I mean, I don't. I'm not trying to say that I do. I'm just like... do you want more talking about specific questions on your homework? If you do, like, paste it or send it to me, or else I'm going to go back to doing some of my time evolution garbage.
You can get in a Discord call if they want to talk.
Oh, yeah.
Hey, honey, you want to come here?
Oh, and...
Oh.
Long... God, she got me with her tail on the way out.
Say hi, Juno.
Yeah. She's not in the mood. Okay. Well, if either of you want to talk more about that homework stuff, by all means, throw me a question either in chat or text me. But otherwise, I'm going to go back to my time evolution.
She's stuck.
So what I was doing previously was I had an initial state that I was given, which was plus. So ooh, wrong color. So the initial state I was given was psi at t equals 0 was minus in the x basis. And what I was trying to do was just do some time evolution here to time evolve the state and find it at a later time t. Like, that's all we're doing in quantum mechanics ever, right? So I was following the prescription for time evolution, which is to time evolve a state, you basically gotta take the state at t equals 0, written in the basis of Hamiltonian, and then throw some e to the minus whatever's on to actually put the time dependence in on each state. And what I got was this last line down here after factoring out a global phase right before the line break, which is, did I mention what the Hamiltonian was up here? Yeah, so the Hamiltonian, I chose a Hamiltonian that was G B naught SY, this thing here, which is simpler than the quantum capstone students were given on the most recent homework. But it is it's a subcase of that homework assignment if you choose a particular value of theta. And I just chose it because it would be easier. So time evolving and putting things in the base of the Hamiltonian, which would be the y basis, I get an expression that looks like that. So I'm just going to like try and copy it down from basically memory down here and see what I can do. So so hey, look at that uptime. Look at me. So psi at t equal, psi of t, not t equals 0, psi of t is equal to, this is going to be nasty. I even forgot what the first bit was going to look like. Oh, there's a 1 over root 2. Okay, now I know. 1 over root 2, 1 plus I plus y minus... Is it minus? My memory is like totally failing me right now. It was a plus. Okay, cool. Great. Plus e to the I minus I t e minus y minus e plus y. And just a reminder, I got this subtraction in the exponent by factoring out global phase stuff. Then this is a 1 minus I minus y. Okay. And my goal now is to ask a couple questions about this, namely, what's this? That wasn't a very specific answer from 8-Ball. You might want to ask it again, Rosemary. I'm not 100% sure about the... Don't test her, Austin. You never know what kind of... how people are feeling about their stuff. What if you're talking to someone who is just so done with... Okay, Austin, you want to play this game, sir? You roll the magic 8-Ball. Should you drop out? You know the answer to that question. I know the answer to that question. You do it. Yes. Now roll the ball. I know you know the answer. Roll the ball. Ask the magic 8-Ball. You tell me what you're going to get. I'll wait. That's a very non-committal answer. Don't bet on it. My point was proven, but not very satisfyingly, so... oh well. Okay, so I'm gonna go back and I want to do a subset of these. I'm gonna do Sx as a function of time and Sy as a function of time. These are the two expectation values I want to calculate. The reason I want to do these two is because this is the basis of the Hamiltonian, so it might be a little interesting and it'll at least be easy to do. And this was our original state that we were given before time evolution was minus x. And so if time evolution did nothing to this state, which it might not have, but if time evolving doesn't change the outcomes of measurement of this state, then we're still going to get an expectation value of negative h bar over 2 when we calculate this guy over here. If time evolving did somehow do something interesting to our state, then this will no longer... She knows what she's talking about, Austin. We just gotta let the Twitch career take off. You just gotta let the Twitch career take off and just pull you through the ether to wherever your soul should go. Which, yeah, 3 times. I'm dead serious. I tell literally every person I know about how damn smart Dave was. I told everyone about Dave. Because it's just like, there were 11 of us at the beginning of our cohort or some garbage, and every single one of those people, except for the robots, knew that Dave was the smartest out of every single one of us. Dave is so much smarter than me, because he was just like, you know what? I recognize that a master's degree is awesome, and I want it, and I don't want a PhD. I'm going to get it in like 2 years, and I'm going to get the hell out. And like... I think it's a lot closer to truth, Rosemary, to say that you convinced yourself to do a PhD and Maggie and I gave you our stories and our experiences being people who probably should not have joined to do PhDs. I've been here 4+ and Bo still hasn't let me do my master's. Man, that's a combination of things. You and I both know that that's not just you. It's a combination of quite a few things. So like, I know because to me that the time that I've been here is haunting to me. And like, I've been here a real long time and I feel that amount of time stretching in perpetuity to be longer and longer. It's not, you think you want to befriend a grad student and then you think you want a PhD? Oh, before you're a grad student? Yeah. Yep. Yeah. Well, I will throw this out there for both of you, that there's nothing wrong with, like, jumping into a grad program and then realizing later that you don't want to be in a grad program and just, like, getting a master's degree and having spent, like, a couple years just getting paid to learn physics, like a year or two to get a master's degree and learn physics. That's an awesome thing to do, and it's a great way to, like, still do physics, to not do anything too scary, but to not fully step outside of the academic cave and, like, have to deal with sunlight, because I'm terrified of actually working a real job. Hence why I'm doing this right now. Job security and getting paid to do physics while being safe is cool. Yeah, and we're also still in the middle of well, not in the middle. We are in an ongoing pandemic state where not only is the job market scary, there's a lot of things that are scary out there, and graduate school is a way to stay in a place that's not scary. For some people. Some people get absolutely brutalized in graduate school and have very unhealthy, abusive relationships with the academy and their advisor and who knows what. You know, like the classic horror story that I tell about people, which is the story of another friend of mine. She had a friend in her graduate program, or that went on. She had a friend who was in a graduate program. And this friend was doing lab work for their PhD for their advisor. And they were not allowed to graduate. And their graduation was delayed 8.5 years. So, like, not that it was delayed 8 years, but it took them 8.5 years to graduate when they were done and ready to graduate at the end of 4. And their graduation was delayed because their professor wanted to keep them in the research group because they provided incredibly cheap labor. And that professor just kept them. And the institution did not punish that professor for doing it because there's no mechanism to really do anything to tenured faculty unless you want to, like, fire a tenured faculty, in which case you are not going to get another hire for at least 5 or 6 years. So bad people in departments stay because what are you going to do? You're going to get rid of them? You're going to be down a professor and now you can't hire a new one. So this graduate student was stuck for many years until they finally told their professor, like, either you let me graduate or I'm out. And they were going to leave after 8 years with no PhD, and the professor was like, oh, fine, I'll do it. Yeah, no, it's a horror story. It's a straight up horror story. Yeah, Austin, Rosemary and Sophia are both undergrads of ours who have previously been either myself or Maggie's LAs. They're good eggs. Until I get the Bach? I don't know what that means, Rosemary. But I've also been teaching for like 4 hours today, and I'm starting to... Oh, bachelor's. Oh. The batch. I read that as the Bach. Oh no, I'm losing it. That's fine. I'm gonna keep doing a little bit of physics here, but... okay. So... Oh yeah, that was fun. Austin, do you remember me telling a story about me covering for one of Mike's studios and getting absolutely ass blasted by someone in the room who was like, I see what you're doing with the women in the room, putting them all at one table, and this is not okay. And like rightfully calling me out for that, even though it wasn't my fault. It was like a professor that did the seating arrangements. Do you remember that, Austin? Do you remember me talking about that? That was yeah, that's Sophia. It's good times, Sophia. Yep, yeah, you remember. Let me just revisit that for a second, Sophia, and say that there was a lot of fallout that happened because of you reporting that to me. So I thank you for being stern about how you felt about the situation, because it did result in some departmental action that was really important to stop that kind of stuff from going on. We did not get our asses handed to us. We were fine. It was some of the faculty. The department. Yes, the department got in trouble for that. And some people had to do some trainings and got told to not ever touch assignment spreadsheets ever again. It was, big oopsie. Real big oopsie. Oh, that's a cute cat.
It has a powerful aura.
A very powerful aura. That's a very powerful cat. It's not going to capture on the camera well.
Yeah, it will.
Okay, she's going for it.
This cat has a powerful aura.
It's very blurry.
I don't care.
It's fine.
Good.
It's a very powerful cat. Okay. So I'm gonna do an expectation value or two here, and then like we'll see what I'm even doing with this. But like I'll keep talking with y'all if you're hanging out for a minute, because like I'm just doing physics here. Okay. So expectation values def look like So this is nasty. Actually, this is the nasty one. I'm going to do SY first because I need to get my brain back working before I try and do the SX one, because the XX one is going to be really nasty. So the SY one, well, in Brockett notation, right, I have to know what a matrix does to a ket as an eigenvalue, eigenvector equation to let the matrix do anything to it, to let the operator do anything to it. But luckily, I have psi of t written in terms of the y basis, and so I know Sy's action on y on this stuff. Sy on plus or minus y gives me plus or minus h bar over 2 times plus or minus y back. And so that's nice. Good luck on apps. Hopefully you get into schools you want to. I remember that. It's a scary time of unknown. Yeah, applications are ridiculous, and I remember I applied to like 5 schools or something, and I got into a couple of them. Not very many. Some of my apps were a little high, and I was hoping my letters of rec would carry me a little harder than they actually did, because my application was not great. Let me tell you, any place that I was applying to that needed the physics GRE, oof, my GRE score was abysmal. Absolutely abysmal. I mean, yeah, I don't think that there's anything, defining about your quality as either a physicist or a person that depends on whether or not you get into grad school. I think that's one of the worst things we do as physicists, is imply that you are only a real object if you have like a PhD. And if you have anything less than a PhD, you're like some weird like test tube physicist that was half formed. Faculty keep telling me that like I'm making that up and that no one says that, but like it particularly it's from faculty that like should know better, that I'm not making that up, and that it's like it's an assumed thing about the environment of the field. Like, it's not that anyone told me that, it's that like the only people you see who are professional physicists have PhDs. The only people who they talk about are other people with PhDs. Your entire education is geared around towards continuing your education until you have a PhD. Like, it's all there. It's all there. Yeah, I applied because I was expected to. I continued on to grad school because I thought a bachelor's in physics was meaningless. And it's not. It's still a bachelor's degree. But like, yeah, it's rough. I would still do grad school again, yeah. Grad school gave me many years of teaching experience that I wouldn't have had otherwise. And like, I was a terrible person when I came out of undergrad, but I was at least decent at teaching, and grad school has given me the time to like really, really just hone all the aspects of teaching. And so, man, teaching on a resume looks really good. So grad schools that pay you to have an assistantship where you teach are really good resume builders, which is nice. I guess it sort of depends on like where you're submitting resumes to, because whether or not you have a good resume for something depends on, what kind of a thing you're going into. But teaching basically looks good everywhere. So this expectation value, now I need a complex conjugate. Okay, so I'm going to do some trickery here. So there's a 1 over root 2 in psi of t. There's a 1 over root 2 in psi of t bra. And so I'm just going to pull it out as a 1/2 to the very front and ignore my 1 over root 2s for the rest of eternity. I have to complex conjugate some stuff. So the complex conjugate of 1 plus I is 1 minus I. And then I get plus y. Plus complex conjugate of this exponential factor is just remove the minus. Oh, you know why you were hearing the pen, Maggie? It's because I wasn't holding it straight enough. Oops. Sorry for having a slanty pen, I guess. That's a Twitter quote. Is there a streaming schedule? I have to hop off to hold office hours. Yeah. So we actually just uploaded a schedule to the about page on here. So if you click about right under the stream or schedule, there's a schedule page. You can click the schedule. I'm probably going to be doing like once or twice a week, just doing kind of whatever the hell I want to. Maggie's going to be doing office hours specific to paradigms and capstones level stuff. I'm probably going to start doing like special topics like information theory, higher level quantum, whatever I want, basically, my research. And Austin is going to, I think, be sticking to lower division stuff that's like relevant for what he's teaching. But our individual schedules are on there, Rosie, so if you want to hop in at any time, you're welcome to, and just hang out. I love being on Twitch and messing around on here. It's a hell of a lot of fun. And it's definitely a lot of fun with people actually talking in chat. But yeah, you don't have to stick around. You can go hold your office hours. You don't feel indebted to being here. But thank you for stopping by and saying hi. And I didn't know that this was your account, but I saw the follow a long time ago. So thank you for hanging out, Rosemary.
Tie friends.
Yeah, and hopefully some of that was at least a little helpful, if not actually helpful. Okay. And so now I need to conjugate this bit, which gets a plus I. And I need to bra-ify this thing. Yeah, I need to... Oh. Yeah. I didn't catch that. But, I mean, I was never a big Harry Potter fan to begin with, so I guess fight me on that. But definitely not now. Definitely not now. Nope. Getting noping out of that. Hell yeah. Get a trans rights in chat. Cause trans rights. But trans rights, hell yeah. I see what you did with the caps lock there, and I actually like that more. Yeah. Bye. Thanks for hanging out, Rosie. Okay. So what's still left here is SY and then all the ket garbage that I need to keep bringing around. So now I just need to write everything as kets. And it's 1 plus I plus Y plus e to the minus I t e minus y e plus y over h bar times 1 plus I, no, 1 minus I. Minus y. Okay. I don't know who all is still in here, but hi to anyone who's in here hanging out. Y'all are, any of whom who are hanging out are welcome to say hi or ask a question about anything I'm doing here. It's quantum mechanics, which is pretty specific as a set of things, and I know it can look a little messy and a little scary, but it's actually a lot easier than it looks. So now what I need to do is I need to let my matrix that I have sitting here, I'll give it a little hat just to remember that it's sitting there. I need to let this matrix act forward on the kets to the right, and I know what the action of SY on plus Y and minus Y are. I know that from my eigenvalue equation up here. So I know the action of this matrix, I can just let it act forward on these kets, and then I get dot product-y looking things. And this is like a 2-line continuation because I ran out of room, so I'm going to like pull this thing way over here. Let's let SY act forward, and I'm going to leave the ket alone. So there's a 1/2 on the outside. I'm going to leave the bras alone for the time being. Did you just post a bar quank? I see that bar quank. Okay, cool. That's fine. It is a fantastic emote. E to the I, T. And like, if you have any questions you can think of, Austin, because I know it's probably been the longest since you've done quantum out of the 3 of us, you can throw whatever you want in chat if you want me to explain anything more specifically. Minus Y. And then SY acting on plus Y and minus Y are going to give me both H bar over 2 with a plus or a minus sign depending on which ket it's acting on. So I'm going to actually pull the H bar over 2 out to just right here. In fact, I'm actually going to pull it all the way out to the far left. And then what will be left in front of plus Y is a plus sign, and what will be left in front of minus Y is a minus sign from the action of SY on those states. So then I get a 1 plus I. Plus Y is just going to be left with plus Y. E to the stuff is still going to be E to the stuff. And in fact, I'm going to call this energy difference now. I'm going to give it a name. I'm going to call the energy difference over H bar omega. Because, so I'm going to say omega naught is defined to be E minus Y minus E plus Y over H bar. Because I'm real tired of writing that. So it's E to the omega naught T And it's actually a minus because that got left over from the action of SY on this state. Boy, that shortened that a lot. It's fine. 1 minus I minus Y. I'm sorry, I won't be on here for much longer. I just want to finish this calculation at the very least. Have some amount of closure to this. Okay. I think I've done this correctly up to this point. So now I just need to take a dot product. All I need to do here is like plus y on plus y gives me 1s, minus y's on plus y gives me 0. So I'm going to get a few terms here. And I'm not going to write them out as explicitly. I can turn that into an h bar over 4 now. I'm not going to write them out as explicitly as I did last time. So I get plus y on plus y gives me a 1, and the coefficients in front of that are 1 minus I times 1 plus I. 1 minus I, 1 plus I. Plus on plus gives me 1, so I don't need to worry about that. Plus on minus over here is going to give me 0, and so I don't need to keep track of that term. Minus on plus is going to also give me 0. Minus on minus is going to give me a 1. So then I get minus e to the I omega t times e to the minus I omega t is going to make the exponential stuff go away. And so what I'm going to get is, oh, I dropped my 1 plus I here, is I'm going to get 1 minus I, 1 plus I. And I got 0 again. Because these two terms right here are going to be the same thing. Once I FOIL them out. They're the same term and I'm subtracting them. So, A minus A is 0. So, why did we get 0? We got 0, if I scroll all the way up, we got 0 when I did this before. I got 0 for my last eigenvalue, or for my last expectation value calculation for the state at t equals 0. And what I find for SY is that I get 0 for all time t. That's kind of interesting. Does that make sense to me? Well, my Hamiltonian is written in the y basis. So I actually expect, and this is actually just kind of a true quantum fact, any operator that commutes with the Hamiltonian, which is to say any operator that shares a set of eigenvectors with the Hamiltonian, and SY definitely commutes with the Hamiltonian because the Hamiltonian is literally a linear multiple of SY. Any operator that commutes with the Hamiltonian should have an expectation value that is independent of time. That's just true, and that's separate from the kind of thing that we talk about where a state has measurements that are independent of time, or expectation values that are measurements independent of time because of the construction of the state, which is called a stationary state. So this is not a stationary state. It has a non-trivial time evolution, but the expectation value is still 0, which is kind of cool. That's cool to me, at the very least. So basically what's happening here is that as I proceed through time, the relative contributions of these two states, why does this happen? The coefficients stay the same magnitude in time for SY. I think that's the argument. So as time evolves here, the coefficients on the plus y and the minus y ket for this time evolved state here, their phases are changing in time, right? And how much of each one is real or imaginary is changing throughout time. That's what this phase does in quantum mechanics, is it's basically changing the realness of your coefficients. But because the states that we are given, because these things are not going to have, like, their magnitudes for those coefficients are the same, and because the states that because the operator that we're looking at, why is this stationary? Why do I get 0 from this?
Why do you get the
Why is my expectation value of SY 0? It means I either messed up a complex conjugate, which I don't think I did.
No. So in the non-time evolved case, it should be 0.
In the non-time evolved case, it's 0 because I'm just as likely to get to measure plus y as I am minus y. In the time-dependent case, I guess I'm just as likely to measure both, and adding that time-dependent coefficient. Oh, no.
Yes, because they're the same energy value, right? No, they have different values?
They have different energy values, but I still found it algebraically to be... I could have dropped a negative? I don't know. I'm pretty sure I got my minus signs correct, and I got my complex conjugates correct. So I'm pretty sure that this is supposed to be 0. So I have a memory that's just like an emotional thing that's stuck in my head for quantum mechanics, which is that in order to get cross terms, you need to be writing a state that is a non-trivial combination of Hamiltonian states, and then you need to look for an expectation value that doesn't commute with the Hamiltonian. So this is something like the
It is the Hamiltonian!
This is the... What I found was the expectation value of the Hamiltonian. And they have the same value of energy. One's positive and one's negative.
That's literally what I said!
Yeah, I didn't catch that. I'm sorry. Yeah, okay. So it should be 0 because, again, this is a weighted average over time, and I still only have 2 possible states, one at energy 1, one at energy 2. They are distributed about 0. One's positive and the other's negative, and they have the same number attached to them for the energy. And I'm asking what my average value is as a function of time. That's what this expectation value calculation is. Well, what's my average value as a function of time if I have the same probability, if I have, root 2 over 2 probability over here and root 2 over 2 probability over here? Well, I mean, if I have 2 possible outcomes that are distributed evenly over 0, and they have the same probability, what's my expectation value at 0? Great. What a great place to be confused. I love it. Thank you, brain, to be panicked about that, because I clearly know what I'm doing. Okay, let's do the other one. So yeah, this checks out for all the reasons that I just said, and yeah. So let's do the other one. This is the one I'm much more interested in. Sx, remember, was the operator corresponding to actually the initial state that we were given, right? We were given the state minus x as our initial state. And so calculating this thing as a function of time might lead to some pretty interesting results. So that is going to be this stuff up here written with x's rather than written with y's. And so, copy, peace. Thank you, OneNote. With an XX in there instead. Look at me. So, unfortunately, I don't know what the action of SX is on plus Y. I could go back and turn this state into the X basis to try and keep my life all nice and in pluses and minuses and keep my life in the nice realm of Brockett notation. It's not that I can't. It's that I don't want to do this. I don't want to do this calculation in this way. This, to me, looks like a great time for matrix notation, because I can just plug these things as columns in, and I don't have to worry about linear combinations or any of that garbage. I can just, go for it. I don't have to deal with any of the shit surrounding finding actual linear combinations. That doesn't exist here. I'm just going to plug these things in as rows and columns and just call it good. Remembering that I made these omegas. So, as a row, keep the 1/2 out front. As a row, my ket looks like 1 minus I in the 1, 0 position. This is in the Y, I have a choice here. I can write down plus Y as my 1, 0 vector, or I can write down what plus Y is and keep all of these matrices written in the Z basis, and I think that's the best thing for me to do. Because if I write down this thing in the z basis. That means I get to use this thing written in the z basis, and I know what Sx looks like in the z basis.
Don't ever write your matrices not in the z basis.
I can write my S. Well, you can either write them in the z basis or in their own basis. Don't ever write something like x in the y basis. That's just like, don't do that.
Well,
so,
you can't do multiplications.
Yeah, so this is 1 minus I. This thing here, right, like you can only do matrix multiplication if they're all written in the same basis. And as long as you don't do anything silly with vector renaming, you will always be working with things that are in the same basis.
The rows have to be the same rows and the columns have to be the same columns.
Yep. Rows have to be the same rows and columns have to be the same columns for you to do matrix multiplication. Yeah, that's a good way to remember that. So this thing really, the plus y ket is really a vector, which is something that I can write down in the z basis. And I have to go all the way back up or look at my handy dandy spins reference sheet to figure out what this thing looks like in the z basis. So plus y in the z basis is 1 over root 2 plus I minus. So this thing is 1 over root 2 plus I minus. That's the vector. So just to be clear, this is a number sitting out front. This is a coefficient to a state. So this is a coefficient. This is the plus y written in the z basis. Just want to be clear about what I've written here. So now I can do the same thing for the next piece, which is 1 plus I e to the positive I omega naught t times minus y, which is 1 over root 2, 1 minus I. And this is, again, a ket, or a broad that's sitting here. This is a vector. This piece is a vector. This piece is a coefficient. And now I need, what I'm going to have on the next line is Sx acting on these things. Well, I have to write these things again as vector columns, but now I'm just going to write them, I'm going to write the matrix in its, like, matrix form. The operator Sx in its matrix form, which in the z basis looks like 0, h bar over 2, h bar over 2, 0. Then that is going to act forward on my kets, which is 1 plus I. So now I have a 1 plus I vector column, because it's a ket now, on 1I, plus 1 plus I, 1 minus I here. 1 plus I, this one gets the minus, e to the minus I omega naught t, 1 over root 2, 1 minus I, as a vector column. Okay. So what I can recognize that this matrix is going to do, this matrix is going to multiply my vectors by h bar over 2. And then what it is also going to do is it's also going to swap the x and y components of the two vectors, right? So if I do a matrix multiplication on an AB vector, this is going to take B and put it in the A spot, and this is going to take A and put it in the B spot. So what this will look like is 1/2. I'm going to pull the h bar over 2 out. Anything else I can pull out? Not really. So it's 1 minus I. And I can also pull out the 1 over root 2s, because there's a 1 over root 2 in every term. I knew there was something I could do. So maybe I'll do this as 2 root 2. Times the vector 1 comma I. I know. I swear it's a vector. Plus 1 plus I. Times 1 comma negative I. And then what Sx is going to do is it's going to swap the two components, and so I can write that thing down as 1 plus I is the coefficient, I1 becomes the vector, and 1 minus I e to the minus I omega t is the coefficient, which you can't even see because I need to scroll up. And then negative I1 is the vector. Okay. And now what I need to do is I need to just, like, do the algebra. So I'm going to keep my 1 over 2 root 2 out in front. H bar over 2. So I guess it's 1 over 4 root 2, but meh. And now I need to do dot products. And unfortunately, I don't get to use orthonormality anymore because these vectors are not necessarily orthogonal to one another. And that sucks. But I just have to do the dot products. So I have a term that looks like 1 minus I, 1 plus I, where I'm taking the dot product of 1I with I1, which gives me 2I. Yes. Then I have another term that is going to be this vector dotted with this one over here, which looks like 1 minus I squared e to the minus I omega naught t. And then 1I dotted with negative I1 is going to actually give me 0. Because 1 times negative I is negative I, plus I times 1 is positive I, and that's the addition of those things is going to give me 0. So I also know that that's going to happen with another dot product in here, namely this one on this one is also going to give me 0 because I minus I is going to give me 0. So that dot product of, just to highlight them in pink, so this dot product with this vector is also going to give me 0. So that's kind of nice. And those are orthogonal vectors, but they're not the basis vectors that like we're used to. So there's nothing special happening there other than the actual math is giving me 0. So that's kind of nice. So then the only other one I need to keep track of is this one times that one, which is plus, ooh, I'm still in pink mode. There's someone else watching. I don't know who that is, but hello, whoever that is. Welcome to Quantum Mechanics, unless it's someone who was already watching, in which case, like, whatever. 1 minus I, it was this one. So it's 1 plus I times 1 minus I times e to the, what did I do? I lost my moderators are not even watching me for errors right now. Tisk tisk. I lost this right here. So there is an e to the minus I omega t right here. E to the I omega naught t right here that I dropped. And it's not actually going to matter in this term. It doesn't matter. In this term, it doesn't matter because it's 0. I don't care if you're building a lamp right now. Wait, is it the nasty lamp? Is it the one you got for a gift? That I shouldn't say was a harsh gift, but like it kind of was a prison sentence to be given. Yeah, okay. Enjoy your lamp building, dude. So this last term is going to be changed by this bit here, which is e to the time dependence went away again. The time dependence went away again. It shouldn't have gone away. I'm allowed to factor out a global phase in my state. That's fine. Why is my time dependence going to go away? It shouldn't. So what's going to happen here is that this last dot product I'm doing, which is this vector, this row dotted with this column, is going to give me e to the I omega t times e to the minus I omega t, which is bad, for the record.
Wait, what row?
Pink row, pink column, this whole bit. So that's a column vector. This is a row vector.
Where your parentheticals, what's the, I can't tell the difference between your vector and your columns.
I said them as I was going. They have commas.
So okay. So that's all part of the coefficient.
This is a coefficient. This is a coefficient. This is the vector row. 1 minus I. So, okay.
Did you conjugate it correctly?
Question. When I went and wrote this bit, I don't need to recollect the... I would need to recollect the terms in terms of the, like, kets to get orthonormality relations. But I don't have to do that if I'm just going to, like, make dot product stuff happen, right? So my problem is that from 1i and negative I1, that dot product is 0. Because it's negative I plus I. That gives me 0.
Isn't that dotting y plus with y minus? So
it's dotting y plus with a phase shift of y minus. Yeah. It's not quite y minus.
That phase shift doesn't matter.
That phase shift doesn't matter. I agree with you. But I'm weirded out that my mixed states that I got from acting SX doesn't... Oh, God.
Did you not act the right operator?
No, it's going to be 0. And it's going to be 0 for a very, very special reason. It's going to be 0 because I picked the one set of these calculations I could do so that I was working with a matrix that is exactly off diagonal with the same components in both spots. What this means is that this, as a mixing matrix, all it's going to do is swap the components. And what happens when I take an orthonormal set of two vectors and swap the components on two of them? I've just done this.
Oh boy, it's the same thing.
Oh boy, it's still an orthonormal basis, and so I'm still going to get zeros, and so I'm still going to get a stationary state for this expectation value. Because I picked a really bad matrix to do. Cool. Okay. Just to give the explicit argument or to talk about what error I just ran into to sort of make sense of what's going on. What I decided to do was to take a state that was originally in plus x, to time evolve it using a Hamiltonian that depended on the y spin operator, sy. So to do that, I then need to take my x state and turn it into sy, and put it in the y basis. And then I wanted to calculate the time-dependent expectation value of sx using my time-evolved state. And when I did that, I don't actually get a time-dependent expectation value for sx. What I get is something, and I'm just going to keep going and see what I get, because I think I'm doing what I'm supposed to be doing here. So the thing that freaked me out is that I found no time dependence. My two e to the I omega t terms have murdered one another. And so they're no longer there. 1 minus I dotted with minus I1 is minus 2I. And lo and behold, I got 0 for this. So there's a couple reasons for this. One, and I think the most important reason that this happened, just as, I guess this is less a comment for people who are doing quantum mechanics, and more a comment for people who are designing quantum mechanics questions to give their students. So I'm not speaking, I guess, at anyone who's watching this that's an undergraduate. I'm speaking at graduate students and professors. I picked a bad state to start everything with. The plus x state is a boring linear combination. And because it's a boring linear combination, I got artifacted zeros for this time-dependent expectation value. If I picked a state that was even slightly more complicated than this, like if it was mostly plus x with a little bit of minus x worked in, then I would have gotten non-trivial linear combinations of these time-dependent vectors. And in principle, this bit with these two bits in pink would not have canceled out with one another. There would have been some mixing going on. You would have found some sines or cosines that you normally do when you do problems like this. I found 0 because I picked a trash state to start with. So in principle, this should depend on time. This should depend on time. No, this wasn't a bow move, Austin. This was me. I made this question. Yeah.
Hey, Bo, how to do this? I don't know. I haven't done it yet myself.
Yeah. Wait. Yeah, no. This was not. Yeah. This was not a question that any of our faculty designed. Well, really, it was close to that. It was I took a question that someone did design, and I made a simpler version of it that actually was simple enough to sanitize all of the interesting features out of it. So what that means is this was not a great question to pick, although in terms of interesting physics to sense make on at the end. This zero, this is really like, let me just be perfectly clear here. This zero is not really a zero. It's really 0 times some interesting function of time. That function of time is sitting in there, but it vanishes because the linear combinations are the same when you turn plus x into 1 over root 2y plus 1 over root 2y minus. Because those coefficients are the same, they're both 1 over root 2's, you get the same amount of like stuff on each component. And that means that when you go and you let the operator actually act on the kets that you have, you're going to get things that are still orthogonal because you just didn't do anything interesting with the state you were given. So this is a very long-winded way of saying that me picking something and going in mostly blind ended up with a question that wasn't exactly perfect. Who knew? Yeah. I think that's probably going to be it for me today. Because I've been, hit me with an uptime, Austin, when you're done fiddling with a lamp. I mean, I can see it on OBS, but, you know, like, give me the good timing. Yeah. Hello to anyone who was watching. I don't know where the viewers are coming from, but if you are someone who is interested in physics or interested in learning more physics, stick around for more content from us. We'll be streaming basically every day of the week at some point. You can check our schedule beneath the stream if you're interested in hanging out. We're typically smarter than I was today. I won't make any promises, but usually I'm a little more on top of it than that was, because that was a bad question. But yeah, we're at least here to be laughed at as graduate students who don't know what we're doing, as all people are. Well, not that the graduate students are. Not that graduate students are all people, but that all people don't know what they're doing.
All graduate students are stupid because they chose to go to grad school.
Everyone who goes to grad school made a mistake. How about I sanitize that to that, Maggie?
Yeah.
Is that fine? Okay. Well, thank you all for those of you who were here and hanging out. Thanks to Maggie and Austin for being moderators, kinda. And you were in the living room most of the time. Don't look at me like that.
I sat there the whole time.
And yeah, thanks for being here and hanging out and asking questions. I will we'll see you next time. I hope everybody has a great night. And stay safe out there, because you know why.